gmail.com और पासवर्ड है CSSC@2204 और CSSC का C कैपिटल है।
नहीं है
YouTube streaming का
स्टार्ट हो रहा है तो अच्छा मैसेज स्ट्रीमिंग होता है
ना YouTube तो
हाँ YouTube पे स्ट्रीमिंग স্যার মিটিংটা কিভাবে যাচ্ছে আর কি আমরা ওই ইয়েতে ন্যাব ওনার আছে হ্যাঁ আপনি এসেছে আমরা ওই মিটিংটা শিডিউল করে দিচ্ছি তারপর যাচ্ছি হ্যাঁ হ্যাঁ
Deputy for Madrid Garden.
আর রেকর্ডিং করে দেবে ক্লাউডে এখন
कैसे लिखा
रिकॉर्डिंग हाँ रिकॉर्डिंग ऑन कर देना ক্লাউড
ইমেল দাও এখনো আমার কাছে তোমার ওই
হ্যাঁ ঠিক আছে আমি ওটা পাচ্ছি আপনার ইমেলটা পাঠানো হয় সরি
না লোকাল আমি ওটা চাইছি না
লোকাল ইমেল তৈরি হয়নি আমার
তোমার জিমেল আছে
হ্যাঁ
আমি জিমেল লিখি
ও আচ্ছা আচ্ছা ঠিক আছে আমি আপনাকে
অ্যালুমিনি
হ্যাঁ ঠিক আছে আমি একটা জিমেল পাঠিয়ে দিচ্ছি
CSSC ऐसे का नाम तो
কিন্তু ওটা হয় কি কিছু দিন
ये है तुमको सेंड कर दिया हाँ
তখন আমরা
अभी मेरे को ये अपडेट करना है
हाँ ये बस इसको जूम फोकस करना है इधर कुछ करना है
नेट कवर कर लेगा वो
हाँ साउंड कैप्चर कर लेगा ये
कैच कर लेगा
कैच कर लेगा नहीं तो यहाँ एक चेयर रख सकते हैं वहाँ पर रख सकते हैं थोड़ा क्लोज सुमन एक वो चेक करनी है ऐसे जी
पास में हो जाएगा
तो क्लोज होगा ना तो सुविधा कैप्चर এখানে রাখো টানো টানো
most welcome. But after this, you have to possible and I need to really try. So inside meeting. I plan to leave around 6 o'clock. Even if I have 5 minutes, I'll like to. But that never caught my attention, and also our eyesight is also behaving very strangely. Eyesight has been going very strangely. So আমি জানি কিছু একটা করে আইসাইট ক্যালটা না মানে ম্যানেজ করতে পারছি না most of the time it is down when reels get missing go missing
today I was panic
there was no connect internet for a long time how come I told you I will be anyway I am leaving for Delhi tonight
I'm just PG connect. Could you please put your phone on vibration mode and so on? Let us begin. This is our annual program jointly organized with ISIAA as well as Stat Math Unit, Kolkata. And this is in honor of Professor Somesh Bakshi, who was a professor and a student, and he did his MStat, PhD, and he was faculty for very long, and he's extremely loved person, very helpful, and so we have instituted this, and I'm very happy that it is still continuing. And today I will first invite our director to say a few words.
Thank you very much, and thanks to Professor Srivastava for organizing this lecture. We've been organizing it over the years, and today we have Professor Sinha as the speaker of this series. SCB, of course, we all remember him. Those of you who were in the department division know much more about him. You've interacted much more with him. I had only very little interaction, but very pleasant interactions. And therefore, I remember him very fondly, his smiling face, constantly smoking. That was his downfall, I guess. His a major cause of his untimely demise. 66 years these days is not really an age to go. But the institute lost a very important personality, a very important teacher in SCB. And I welcome Professor Sinha, and thank you very much, sir, for agreeing to deliver this talk. I'm sure all of us, all of the people here are eager to know more about what you have to say today, so I will not take any more time. Welcome once again, and this is your place anyway, so welcome back. Thank you.
Thank you, Dr. Gundubal. Well, this is in a sense my place, as he said. And Somesh, as I knew him, Somesh Chandra Bagchi, that is SCB, he was just Somesh to me. I first met him when I spent 1 month in early 1982 in ISI Kolkata for some reasons. I spent here. I don't know whether there is anyone who remembers that. I don't recall who was there at that time in SMU. I remember
I was definitely there, he was there.
But I remember Ashok Roy and JKG, of course, who was, I think, head of the MathStat at that time. And I distinctly remember Somesh being present in my talk when I delivered a talk in the SMU that one morning. I was kind of new in ISI then, and more so still in ISI Kolkata, because I was in ISI Delhi at that time. I came to know Somesh much better when I came to Calcutta ISI as the director, and in 2000, and I leaned on him on many occasions for advice and help. The kind and gracious person that he was, which is a rarity these days, even amongst academic fraternity, I must say. He gave help generously and hesitatingly. He had that famous smile. Whoever knew him well will remember his famous smile. A kind of shy smile, which to a large extent was his hallmark. In fact, I would go even further and say that I have probably not met many people who is so humble and self-effacing as Somesh was. I can only wish that I had known him earlier and better. So maybe today I try to make amends by dedicating this talk to his memory. Okay, so this is about traces in operator theory, which is engaging my attention for the last several years, off and on. So now, this I just do up and down. Okay, so let me start with definition of traces, but this one is my schedule is for a moment. This is the definition of trace in a finite dimensional Hilbert space, which everyone is well familiar with. Now, what are the basic properties? That this is independent of the choice of the orthonormal basis. When B is for orthonormal basis, I have not always explained these acronyms, but to many it may be familiar. And it has a trace property, or equivalently the unitary equivalent. Independent of the choice of the orthonormal basis. When B is for orthonormal. First question that anyone meets is how to extend this definition in an infinite dimensional Hilbert space. And as I would often tell the students in the class, by the way, this is a point where there are grave errors in many well-known textbooks, including one by John Conway. I'm sure many of you are familiar with the name Conway. To follow Lebesgue, I would advise to follow Lebesgue, follow the master. So what he did while introducing his theory of integration at the beginning of the last century is to deal with the positive functions first, and there was a reason for it. So similarly here, we would like to start with a positive operator first. So let A be a positive operator defined in the Hilbert space and define this infinite sum. Now, someone will say, is it countable dimension? We'll assume for simplicity countable dimension. So this is a sum of positive numbers, so either it will converge or diverge. There is no third possibility. So we'll accept infinity as a value if it diverges, plus infinity. In either case, it is easy to prove that it satisfies both the property, namely it is independent of the choice of the orthonormal basis. The next question, which Lebesgue faced also, is how do I expand this class? If we just restrict ourselves to positive operators, then we are not really having much freedom. Secondly, we want to have some kind of a linearity. Okay? So with positive things, you can't have linearity. So how do we do that? So for that, I'm skipping a lot of intermediate steps because my main interest is not to dwell on the definition of trace, but rather to see what is the utility of the concept of the trace. So one does, just as Lebesgue did, have a concept of an absolute value of an operator. In his case, it is absolute value of a function, and then define A, an operator, to be traceable or trace class, as it is today called, if the absolute value of the operator has a finite trace. Now, how to define an absolute value, I will skip over because then I will not get hurt. In such a case, just as Lebesgue proved, this trace defined by the infinite sum, as we started with the finite sum, converges absolutely and satisfies the two above property. Okay? And then we can set a kind of a norm trace of the absolute value of the operator as the norm of A in this particular norm sense. Then you can show that this class of traceable operators form a linear space. That's not an easy proof. In fact, it is a Banach space. It is complete in this trace norm. And then, Chatin was an assistant to von Neumann. They use this definition. They are called von Neumann-Chatin classes. So P norm you can define, just as Lebesgue defined the LP norm as so. Namely, you take the pth power of the absolute value of A, and that should be traceable, and then the trace norm, P norm will be defined by the pth root. Then it has a lot of properties which are just like Lebesgue spaces. Okay? They are called often BPs or CP. They are two-sided ideals in P of H, which I have explained in the next sentence. That if A is in BP class and B is B, then AB and BA are both BP, etc. So dot 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 means I'm skipping a large number of properties, so that's not my main interest. and every trace class operator is compact. That means they're kind of an infinite dimensional matrix in some sense. That is, it has only eigenvalue except for 0. There is no accumulation point except at 0. On the other hand, there exist many examples. Now, I'll give one in a little while of bounded or unbounded operators with only continuous spectrum, no eigenvalues whatsoever, such that their product has only eigenvalues. Cannot so only, it has only finite trace. So let me give you an example right away. So the Hilbert space is the Lebesgue space L2 of R with respect to Lebesgue measure. The Q is the multiplication operator by the coordinate function, coordinate variable, and P is essentially a differential operator, appropriately defined. I won't spend time on the appropriate definition on it. It can be shown they are both self-adjoint operators with continuous spectrum, which is the whole of real line. Now let delta ns be bounded subset of R, and let that the double bar be the Lebesgue measure of R. And consider the characteristic functions delta, chi delta, and chi s, and form by functional calculus chi delta of the operator Q and chi s of the operator P. So two non-commuting bounded operators with only continuous spectrum. But surprisingly, the product is trace class. Chi delta times chi p or chi p times chi delta, the trace class, that is, has only discrete spectrum. And more surprisingly, trace of the product is proportional to the product of the volume or the Lebesgue measure of the respective sets. So this result is valid in very, very wide circumstances, with the constant changing depending on the dimension and such things. Now, this is the first thing that I met for the first time in my professional life. At that time, I was, of course, very young. I would say it was in the late 60s that I saw this, or mid 60s maybe. And it was a real surprise to me and shock to me at that time. Of course, that was a long time back. Now, there are two genres of such trace results I will discuss here, mostly through examples. Analytical in origin, but one having some either real or complex geometric underpinnings. The first one is known as Crane's theorem. Crane was many people, you are familiar with Crane, and their two brothers, they were, and I think M and S Crane. The MG Crane was a more famous one. It's just like the Riche brothers. There were also two brothers. One was more famous, other was less so. So the one who was less so actually left Szeged, where Friedrich Riche was there, so that he won't be enveloped in the famousness of his brother. So he went away to far off northern countries in those days. That is, I think he went to Denmark.
Is Klein same as Klein Millman?
Yes, the same Klein Millman.
And which is the famous one? I mean, the famous
that is
one.
The famous one. MG Klein, not SG Klein. SG Klein is the brother. Riche also were another two brothers like that.
Yeah.
So what was Crane's theorem? Crane's theorem says the following. Let A and B be two self-adjoint operators in a Hilbert space, such that B is traceable or trace class with the symbol B1. Let phi be a smooth function, complex valued, of compact support. It could be a larger class, but I am not interested in enlarging the class here. So then you prove immediately phi of A plus B minus phi of A is traceable or trace class. And that is not the interesting part. Interesting in the formula that follows. Trace of the difference is related to the derivative of the function. And there is a characteristic function which appears there, xi function, which is called Crane shift function. It is a unique L1 function, which depends only on the operators involved, A and B, with this property that this L1 norm is bounded by the trace norm of characteristic function line here, line lines.
Any question? Someone have any question?
So this is known as a Crane's theorem, and it is kind of a mean value theorem under trace. So that's a way you can sort of interpret it. Original proof of Crane used a determinant, concept of a determinant for an infinite dimensional operator. What can this be? So to give an idea of what kind of possible definition of determinant that you can think of in an infinite dimensional space, as a natural generalization of what you learned for matrices, you can think of this relation which everyone learns when one learns the determinant, definition of determinant, the relation between the determinant and the trace via exponential formula. And use this if you can. And you can in many situations. For example, I have given one. Determinant of, notice the form of the operator, identity plus t. And you define it as exponential of the trace of the log of 1 plus t. This makes sense whenever log of 1 plus t you can define in a meaningful way. And you can whenever t is traceable. So if t is trace class or traceable, then determinant of 1 plus t is definable in an ambiguous way in an infinite dimensional space. Now there have been many more variations of this determinant definition, but this is the most natural one and the simplest one. Armed with this, Crane used, and one uses the Hedlow's representation theorem for complex analytic functions. In particular, he looks at the logarithm of the determinant of this function as a function of complex variable z. And then he obtains this function, which I wrote the formula, the xi function, xi t, essentially as the limiting argument of the determinant function. The argument of that complex function as you come down to the real axis from upper half plane. So that is roughly the proof of Taylor's Crane's theorem. I mean the idea of the proof. Now one can ask, of course, this is just the first order theorem. What about the higher order Taylor theorem-like theorem, asymptotic expansions? This has been proven relatively recently. And so, for example, I give you one second order formula. That means up to the second order. How will it look like? So let A and phi as before. And notice B was, for Crane's formula, B was traceable. That was the hypothesis. Here B is in the Schatten class B2, corresponding to the Lebesgue class L2. That is, means essentially this is the Hilbert-Schmidt class, because Hilbert with Schmidt introduced this class without calling it, of course, Hilbert-Schmidt class. That is, the sum of the eigenvalues of singular values square is summable. Then this is what you show. You see, in the case of the Crane's formula, we stopped in the first order, but now you go to the second order, so we have to take derivative of the function. How do I take a derivative of a function of an operator? So that's the Frechet derivative on an infinite dimensional space. That is, you use the topology of B of H, the norm topology of B of H, and take the Frechet derivative of phi at A. That's a linear map on B of H. So act it on B. B is an operator. So that becomes a, so it is a map. So the pressure derivative is a map from bounded operators to bounded operators. And that has the second order expression in terms of the second derivative of the function phi and a characteristic function eta. Eta turns out to be non-negative, etc., but those are more details. So this is one general function, one general sort of ideas or analysis that one can do or one has done. Now one can naturally ask, instead of going to one variable higher order expansion, one can instead ask, what happens to two variables? If you have not one operator, but two or more. So this is the problem. So H is a tuple, H1, H2, and H0 is another tuple. So there are pairs of commuting tuples of operators. And phi is a, there are two functions, phi j, phi1 and phi2. Now it's a function on two variables, R2 to C. Smooth compact support, let's say for simplicity, such that each of the differences are in the second Schatten class or Hilbert-Schmidt. It's not difficult to show that this product, that may take the function of two operator variables, take its increment, and take another function of two operator variables and take its increment. The product is traceable. But can we compute the trace? Get a formula? Answer not known, even today. Can one have a nice formula like this? This is what is sort of conjectured or believed, or one has at least some examples of it, but there is no general proof. The trace has this formula. The Jacobian of the two functions, phi1 and phi2, and then times a characteristic function xi of two variables now, and or more generally decommuting tuples. So one naturally thinks of a generalization. Can one look at this problem? Namely, you have d tuples, two d tuples such that pairwise differences are in the Schatten class BD. So this is the number of tuples. Then the product of the differences or increments on each function is trace class or traceable. And this is independent of the order in which you take the product. That also has to be proven. I mean, that is easy to prove. That can be proven. That this product can be taken in any order and it is in trace class. But more importantly, that part is easy to prove. But what is not easy to prove is to get a formula like that. It's a conjecture, it is an unsolved problem. So this is one general problem involving traces. Now notice the left-hand side is an object depending on functions of commuting tuples of operators. And the right-hand side is just an integral, so very classical. The question is, the left-hand side, you have something which you can interpret as some kind of a volume element of non-commuting operator system. Now let me go to another genre of examples in complex geometry. Here, Barger, Shaw, Hilton, Howe, these are the main names. These are the people who essentially started it in some way, mostly by accident. So this is a very important part of the observation, going back to, I think, 70s onwards. The almost, see, normal operators were very well understood. Just like normal matrices, you can diagonalize them and everything was known about its spectrum. So he introduced concept of what are called operators which are not normal, but not too far away from normal. One of them he called hyponormal in infinite dimensional filter space. Hyponormals are those where the commutator of T star and T by the people, practitioners of this art, they call them self-commutators. I don't know why they call them self-commutator, but that's the name which has stuck. So, see, T star commutator T is non-negative. That is the definition of hyponormality. And surprisingly, in 60s, late 60s, were already known that it has some properties of normal operators. For example, so these are non-self-adjoint operators, so their spectrum would be part of the complex plane, compact in complex plane. So the real part of the spectrum is the spectrum of the real part. And similarly, imaginary part of the spectrum is the spectrum of the imaginary part. This doesn't happen in general. For normal, it is true. But what he showed that it is true for even operators which are a little bit away from normal. But big surprise is the Burger-Shaw theorem, which says that if you have such an operator, which has some cyclicity assumption, which is explained there, that means the powers of the operator acting on a finite number of vectors spans the whole space, essentially, is dense in the whole space. Then this operator is traceable. Positivity and certain finiteness of cyclicity seems to force the commutator or self-commutator to be trace class or traceable. And not only that, the trace has an estimate, namely it is the multiplicity divided by pi times area of the spectrum of the operator. So that's the remarkable result. You see, forgetting the cyclic part, if for normal operator, I mean, for example, a disk, the area will be exactly pi, unit disk. So the right-hand side bound seems to be bounded by the things coming from the unit disk. I would say more of that. Unlike in Crane's theorem, here infinite dimensionality is essential for meaningful statement. Otherwise, left-hand side will be 0, and you will have really nothing to say. 0 is less than equal to some positive number, and that has no content really. Next is Hilton-Howe type theorem, which is if the commutator is trace class, then take two nice functions, but now on complex plane of compact support. Then their commutator, so you form functions of T and T star. T and T star do not commute. So what do you mean by forming functions of two non-commuting variables? That's a good question. Okay? But as you can realize probably after a little reflection, that the order will not change the conclusions. So this commutator is traceable or trace class, and there exists a unique non-negative L1 function on the complex plane with the Lebesgue measure, that's what I mean, on the complex plane, area measure, such that this formula is valid. This is called Hilton-Howe formula, which is the trace of the commutator of functions is given by the Jacobian of the two functions times this characteristic function R, which is a function of two variables. But it resembles a lot like what you would expect from the Crane's formula, but no one knows so far what is the possible relation between the two formula, except that they look similar. Next question one asks, can one extend this concept of hyponormality, namely the self-commutator, T star commutator with T, to higher dimension, complex higher dimensions? So when phi was just z bar, phi function of z bar alone, and psi was a function of z alone, then the corresponding formula will be trace of T star T, that is a self-commutator, is equal to the, because Jacobian will be 1, so just R function is less than equal to the constant times area of the spectrum of T in the complex plane. And the right hand side maximum is attained in the Hardy space on the disk, open disk. So that is the comment I was making earlier. Let me be a little more specific here. So look at the Hardy space over the open disk, unit disk. And let the operator T, so this is the explicit example where the maximum is reached. T is the multiplication by the coordinate function Z, and multiplicity is 1 because the powers of Z generate the whole Hilbert space. So sigma, the spectrum, sigma means spectrum, I should have said that earlier. Sigma means spectrum is the closure of the unit disk, the closed unit disk. And you compute the commutator of T star and T explicitly because everything is explicit. And this is turns out to be the projection onto the one-dimensional space spanned by the constant function 1. Therefore, trace of the left-hand side is 1. And right-hand side, area of the spectrum is exactly 1. The spectrum is the unit circle, unit disk. Therefore, this R function is exactly 1 for this specific Hardy space example. The question is now, what can we do about higher dimension? So this is something we tried. So let me mention this. So let T1, T2, Td be commuting D tuples of bounded operators such that the T1 is commuting with T2, etc. But T1 does not commute with T1 star or T3 star, for example. So they do not commute with the adjoints of any. The first attempt was by someone called Athavale, who is, I think, right now in Bombay, IIT. He was in Pune earlier. He called it a strong hyponormality, where you look at it this way. Look at from all the commutators, Tj star Tk, J and K running from 1 to D. So think of matrix of operator, D by D matrix of bounded operators in the Hilbert space, where each element of the matrix is an operator in infinite dimensional space given by this commutator Tj star Tk. That's a map between direct sum of H to direct sum of H, d-fold direct sum of H. So this is a matrix of operators in infinite dimensional space. Now this is, if that is positive, or positive definite or not negative definite, I am meaning it in the interchangeable way. He called it, and people call it strong hyponormality of D tuple. And weak hyponormality is when you call a D tuple, commuting D tuple, weakly hypernormal when this complex combination of these P's, D tuple, is hypernormal as a single operator in H. For every non-zero complex number, complex D-fold number is alpha 1, alpha 2, alpha d from C, then you call it weakly hypernormal, or sometimes people call it projectively hypernormal. Obviously, strong is stronger than weak, but sadly, none of these two definitions lead to any kind of trace results. There is a counterexample immediately you can construct, namely here. So this is one of the simplest two variable problems. Take by disk D2, unit disk, and look at the Hardy space on the by disk. So Hardy on by disk, and take the tuple, call it M1 and M2, multiplication by the coordinate Z1 and Z2. Multiplicity is 1 because all the polynomials Z1 to the power K1, Z2 to the power K2 acting on 1 generate the space. So multiplicity is exactly 1. But it now compute the self-commutator m star m. It is a 2 by 2 operator matrix, and it is easy to compute explicitly. A simple example, and it turns out to be this diagonal operator matrix, which looks like the projection tensor identity, and the other one is identity tensor projection, or P is the projection for single variable to the constant function 1. This is a matrix 2 by 2. The operator is not even compact. Okay. So forget about trace class. So this is a clear, simple counterexample. It is positive. Look at it. By looking at it, you immediately decide this is a non-negative matrix, operator matrix, but it is not trace class. The Barger-Shaw theorem in general is false in higher dimension. You must have further conditions or something. So 22, that is last year, I guess, Galadhar and I, along with the student, we tried to look at it. And we found a set of conditions, but still not completely satisfactory. But nevertheless, but I should have said that in between, that is some years back, Douglas made an attempt. Douglas, along with Ian, maybe one of his students or certainly collaborator, they improved on earlier work, but they had a very strong assumptions, which I want to mention briefly. So again, as I said, let T1, T2, Td be a commuting D tuple of weakly hypernormal operators. Assume that this is finitely polynomially cyclic. That means this, the linear span closure of all the possible polynomials acting on finite number of vectors I1 to xim is the Hilbert space. So they generate the Hilbert space polynomials in these D commuting operators. And also they assume that the Krull dimension of this quotient, all the polynomials quotiented by this vanishing ideal of T, as it is called, is 1. Then they showed that each of the commuters, Tj star Tk, J and K running from 1 to D, is trace class or traceable. So this ideal is, of course, those polynomials on with the T1, T2, Td vanishes. That is an ideal. Heuristically, that above, so assumption that the Krull dimension is 1 is a rather strong one. It is not clear how to relate it with the spectral assumption, but in some special cases you can relate it. That means there are relations between these D operators such that one can reduce the problem to much lower dimension. That's what actually they do. So you can observe that any linear combination of these operators is also going to be hypernormal and finitely cyclic, and then they use Barger-Shaw theorem for each to get the result. In other words, they have not really dealt with the multidimensionality. They have reduced the problem to one dimension by this extra hypothesis of the Krull dimension being 1. Roughly speaking, the assumption implies that the joint Taylor spectrum, that means the simultaneous eigenvalue, you put block of eigenvalues, so you have D matrices, let's say, they commute. So they will have joint eigenvalues. A collection of all D tuples of complex numbers forms the joint Taylor spectrum for matrices. But for arbitrary operator, there is a corresponding concept that is called the joint Taylor spectrum. That lies in an algebraic curve or is very thin, in other words. But this is a d-dimensional object, so the spectrum should have been in CD. But actually, their assumption means the spectrum is on a very small subset of CD. And that is why they are able to handle it. And that's a very strong assumption which cannot be really verified in any realistic examples. So instead, what we did, or we tried to do, I mean, it is partly published, but it is work in progress. We introduced a map like a determinant, but it is an operator to operator map, not operator to complex number map, like normal determinant. So it takes bounded operators on matrices, on D copies or operator matrices, same thing, and maps it to a single operator in the Hilbert space. And this is the way you do it. It is a combinatorial thing. The signum is just the signum function parity of the symmetric group. So you take symmetric group in these symbols and use these sigma and tau to turn the indices around. Okay? And that is the way the expression is. It is a completely antisymmetric symbol, just like determinants are supposed to be, except that it repeats it, because now let me use the board for a minute. You see, the simplest thing is you can try looking at 2 by 2. That's the simplest case. The positivity a posteriori implies it has to be at least self-adjoint. So which means A and C has to be self-adjoint, and B star will appear. If B is there, B star will appear to make it self-adjoint. So that's the minimum condition. But now the positivity, I want this to be positive or non-negative, will imply this. Of course, if C is invertible and so on, otherwise you'll have to do some other trick. But assuming C is invertible, this is what you will get. Okay? Imagine if things were commuting, then you would have got and that means, so that's the positivity of old determinant. So avoid this lack of commutativity, we have to symmetrize the expression. So it is kind of symmetrized Laplace expansion, if you like. The Laplace expansion for normal commuting symbols, here they are non-commuting symbols. So we'll have to use some kind of a symmetrization of the Laplace expansion of a normal determinant. And to make it a self-adjoint object, that's the first thing you will need for a positive object. The main theorem is this. Let T be a commuting D tuple, that is T1, T2, TD, satisfying this determinant which I had just defined earlier, okay, as a kind of symmetrized Laplace expansion to be non-negative. In other words, that is my definition of hyponormality for D tuples. And let that be M polynomially cyclic, that I had already defined. That means T1, T2, TD, you take polynomials in T1, T2, TD, they are commuting anyway, but then you apply it on say M vectors that generates the whole space. M is the so-called multiplicity or cyclicity index. But there is one more technical condition. I don't want to spend time on it because it is too technical, but we need a condition. But that is not as strong as Douglas-Ian of making the spectrum squeeze into one-dimensional subset. Then this determinant is traceable, and the trace is bounded by this. This is the best we could achieve at that time. On the right hand side, we could not, and we have not yet proven that right hand side has a better bound, namely related with the Lebesgue measure of the Taylor spectrum of D tuple. That is the aim. is to relate the bound with, in fact, we want, so we have conjectured and we would like to prove it, that the right hand side can be further estimated by that estimate m by pi to the d factorial times Lebesgue measure of the Taylor spectrum of the T tuple. T is a T1, T2, Td as a subset of CD. So Lebesgue measure on CD. And for next thing we could do, of course, is to take a simple case and explicitly compute it, namely, just as we did for disk. In this case, D unit ball, take the open D unit ball, D-dimensional unit ball, take the Hardy space on it, and take the multiplication operator by the coordinates, not coordinate function, I should have, okay, coordinate function, the coordinate, in the Hilbert space. Then as before, the multiplicity is 1. You can compute the determinant explicitly, on negative. Its trace you can compute explicitly, just 1. Since the volume, so it will be the spectrum will be of this D tuple, commuting D tuple is the spectrum of the closure of the D unit ball, D-dimensional unit ball. And that is pi to the d by d factorial, and that is exactly why you get 1. So that is the factor here. So that is exactly what we would like to prove, but we have not yet proven that, except we have proven half of it. Namely, we have proven that this is trace class, and we have an estimate for the trace, but we have not gone the last mile, namely to relate the estimate with the Lebesgue measure of the spectra, of joint spectrum of the operators involved. So basically the message is that you have a classical object on the right hand side. By that I mean you have the sphere, or you have the disk, you have multi-disk, or you can have unit ball and more complicated objects. That allows you to compute the spectrum, compute the volume, and that is related to the spectrum. And the left hand side, you have non-commuting objects, because remember, this is a matrix determinant of matrix operators of T star and T coming out of T star and T commutator. That is related to the Lebesgue measure of the Taylor spectrum of the operators involved. So this is the message that I wanted to give, is that there are sort of, in a sense, when you begin, it is not expected to have any kind of relationship. And I think I will end with that it is often worthwhile to pursue with unexpected relationships, which often appear. Though you get hints from somewhere, but it is for people to investigate further and see whether you can discover more unexpected relationships. Thank you.
Any question? Any question from the yeah, please.
Last year, we have similar estimate for matrices, known for matrices.
By matrix, you mean finite dimensional?
Finite dimensional matrix.
Finite dimensional, everything is.
I mean, inequalities like that.
You mean
not the Lebesgue one is only 0, but the other one is 2.
no, this is not 0, because this is a tuple.
That's it.
Under bar is means a tuple. Okay, you have so on. So there will be cross commutators and so on. So this is not a No, I don't think there have been any computation for finite-dimensional object because there is no geometry immediately clear background of it. No, there isn't.
One result can it be?
One dimension is the burger shop.
Is that can be used for?
Yeah, this is Gadadhar.
Oh,
Can
God.
I ask a question? Yeah. Yeah, so I meant to talk to you.
There is a question going on already. Huh?
Oh, okay, okay,
It's
all right. Yeah, so,
His voice is not coming in the.
Huh?
His voice would not come here. That's the problem. I mean.
Oh,
Because he's
But
not.
let him finish, then I think we will do that.
okay.
I'm saying for one variable you have Lebesgue of sigma t instead of this norm integer here. Right?
Yes, that is one step further. You see, the proof, okay, let me say that the original proof,
This is for one variable. This is not exactly give the burger.
which one? Our estimate, that's true, yes, because it stops there. No, you see, the original proof of Berger and Shaw is rather complicated. Okay? I don't think I really understood it properly. But the proof that we followed or we tried to understand and follow was due to Voiculescu in the one-dimension case, okay, where he does a trick, which is on the right-hand side, where he relates the norm. You get a norm, that is the first step. Okay. But then to estimate the norm in terms of the area, he has a way to do it, a trick to do it, which does not apply immediately to higher dimension. You're right. I mean, there is a work there in between when in one dimension. Yes. Yes.
Yeah, Gadadhar, go ahead.
first of all, I'm sorry, sitting here, I didn't realize that there was a question going on. So my apologies, but I just realized, hearing you talk about the Crine formula and the Helton-Howe, it sort of looks like, as you have said, the determinant is a special formula, which is you can write down the same kind of a sum when the when the operator tuple is not even commuting. That's what Helton and Howe do. Their formula talks about a functional calculus for a tuple of operators which are not necessarily commuting. Okay, and in general, they come up with a formula for the trace of a function of a non-commuting tuple of operators in terms of an integral of the derivative, some kind of a Jacobian of that function. So what I'm trying to say or ask you is, has anybody ever compared the Crine's formula in one variable and the Helton-Howe formula?
Well, can I answer?
Yeah, sure.
Well, I'll try to answer to the extent possible because, as you know very well, there is a little bit of murkiness here. I have talked to you infinite number of times.
Right.
That Helton-Howe's original paper,
Yeah.
mostly is unreadable.
Yeah, sure. I mean,
I would love to have someone give me a seminar on it, but I have not found anyone, certainly not in India and even abroad, who is willing to risk to give a seminar proving every little line that he has written. I have not met either of these two gentlemen.
Who is this person?
Helton and Howe. These are two gentlemen.
Oh, and they have written such a paper.
Quite some years back. Yes, they've written together a paper. Okay?
It is highly respected and, referred to all the time. Apparently goes into defining all kinds of things actually. But yeah, please go ahead. Yeah.
Yes, but I don't think anyone has explained subsequently properly. I don't know of any.
Yeah, so that of course remains. We have made some attempt at understanding it ourselves.
Gadadhar, your dear friend Putina did not dare it.
Right. No, that is why I was saying, let us get Helton to come and explain. He is almost willing to, but we'll see. Yeah.
I am willing to listen.
Yeah, right. Yeah. No, I actually once talked to him and I sort of said, why don't you come and so on. So he is almost willing to. Hopefully we'll get a chance to, do it. Yeah.
See, we'll try.
Yeah.
Are you done, Gadadhar?
Yes. Thank you very much. Yeah.
Any more questions, sir? Achay, Aditya? Yeah, it seems there is no more questions, and let us thank Professor Sinha for taking
Can I escape for a few minutes?
of course,
Okay.
on her majestic service. আমি আপনার শুনে লাগছি
হ্যাঁ, আপনি আমাকে ফোন করে দেবাশিস, হ্যাঁ, কাল দেখা হচ্ছে।
Sorry, I may have asked them a stupid question, but I was curious. Dr. Rao getting the same night or about that when
I probably haven't read it.
you have not read.
I'm not ready even. I sent you 2 days ago. If you can read it today, I will read it.
Kalka
They were wanting everybody to know that there is tea and